Take a look at Australia from space. Nothing unusual, right? But now, focus on the northern territory of the continent. If we imagine it through magnetic sensors, we notice, whoa, see that? An unknown, strange thing that mirrors the outline of Australia itself. It looks almost the same, but smaller. It's like a twin of the continent hidden deep within it. But what is it? Volcanic lakes? Gold deposits? No, it's something far stranger. This is a magnetic anomaly. Yeah, you're probably confused, but let's find out what's going on with Australia. So, there are devices called magnetometers. They measure magnetic fields, and geologists use them for many things, including exploring the interior of our planet. The magnetic field comes from various metals and minerals buried deep underground. It travels upwards, and scientists' sensors detect it. One day, they equipped aircraft with these magnetometers and flew over the northern part of Australia. When they processed the data and identified a magnetic anomaly with clear geological boundaries, whatever lay in Australia's interior was emitting magnetic signals and followed the outline of the entire continent. And because these signals come from deep rocks, scientists think that valuable resources, including minerals and metals, might be hidden there. But beyond potential resources, what else does this tell us? Inside these rocks, there could be volcanic materials formed over 1.5 billion years ago, minerals that formed long before the dinosaurs appeared. This entire mass of material could tell scientists about our planet's history and how the Australian continent was formed. Okay, that sounds cool, but why are those changes in the magnetic field they detected called an anomaly? Why is it magnetic in the first place? And how does this magnetism work? To understand, we first need to grasp what Earth's magnetic field is. And this is one of the most amazing and mysterious things in the world. The magnetic field is invisible, yet without it, we couldn't exist. So, in simple terms, Earth's magnetic field is our protective blanket, shielding us from cosmic radiation, charged solar particles, and the solar wind. Without the magnetic field, our Earth would be like Mars, a barren desert where life most likely couldn't have emerged. But where does it come from? The magnetic field is generated deep within our planet, where molten nickel and iron create electrical currents. Combined with our planet's rotation, these electrical flows generate the magnetic field that protects us. In addition, minerals and metals inside rocks can produce magnetic fields too. But what exactly is this force? Take two magnets from your fridge and try to push them together. Feel that resistance? That repulsion happens because their magnetic fields are interacting. In some places, this magnetic field can be weaker, and in others, stronger. This means that deep within the planet, in those locations, there are geological processes happening that change the stable behavior of the magnetic field. These places are what we call magnetic anomalies. One of them lies beneath the northern part of Australia. However, the magnetic field is more than just a blanket. Thanks to it, many awesome things happen. For example, a compass needle always points north because the Earth's south magnetic pole is located there, attracting the magnet. Don't confuse the geographic and magnetic poles. The geographic North Pole is in the north, near the magnetic South Pole. It's not just humans who use the magnetic field for navigation. Animals can do it too, without any instruments or technology. Some animals sense the magnetic field, and this superpower is called magnetoreception. This ability helps animals during migration. That is, they know where north and south are. So when it gets cold, they can fly to where it's warm. For some turtles, magnetoreception helps them remember the location of feeding areas. Pigeons have a unique perception of the magnetic field too. In simple words, the magnetic field is also a giant navigation system for many creatures on Earth. Few people know, but we actually have a second magnetic field. In 2018, scientists published research describing how ocean tides create another magnetic layer. But why hadn't we noticed it before? Our main magnetic field, generated by the planet's core, is very strong. Its radiation extends into space and is easy to detect. The magnetic field from tides is almost 20,000 times weaker. How does this field affect the main one? What are its properties? Scientists continue to study these questions. Also, the magnetic field can control the brain. In 2017, scientists used magnetic fields to remotely activate brain cells in mice. Magnetic forces were directed at the parts of the mouse brain responsible for body movement. In this way, the scientists could make the rodent run, freeze, and turn around. But don't think this was done just for fun. Experiments like this can be very helpful for humanity. If you can make a small animal move, imagine what other changes might be possible in the brain. Improving psychological state, for example. Potentially, you could instantly switch from a bad, depressive mood to a happy one. This technology could help treat many diseases related to the brain and nervous system. You might think that such a technology could control you, but don't worry. Magnetic fields pass through your tissues with almost no effect. But then, how did they manage to control those mice? Scientists simply implanted tiny magnetic particles into the animals' brains. Under the influence of a magnetic field, these particles heated up and triggered the activation of neurons. But the coolest thing happens when the magnetic field collides with the solar wind, generating electrical currents and magnetic forces. At the moment, a true cosmic storm happens in the sky, and we see it in the form of beautiful auroras. Such storms are not only beautiful, but also destructive, as they can disrupt the operation of satellites and electronic devices. Sometimes this can lead to minor glitches in your GPS or internet connection on your phone. But there have been cases where magnetic storms were so massive, they led to catastrophic consequences. One of them occurred in 1859 and is known as the Carrington event. On September 1, 1859, an amateur skywatcher, Richard Carrington, noticed a sudden bright white flash on the sun. It turned out this flash was a massive ejection of plasma from the sun's upper atmosphere. About 17 hours later, part of this energy reached our planet and struck as a powerful storm. All telegraph systems at the time went down. The northern lights were visible not only to residents of northern regions, but also in the tropics. For many people who had never heard of or seen the northern lights, this was a real surprise. What must they have thought? The end of the world? Unknown forces from space? Many were undoubtedly shocked by the spectacle. But the real shock was inside major cities. Communication between telegraph systems was stopped. The world was plunged into an eerie silence. Sparks flew from telegraph machines, causing fires in some places. People couldn't send or receive important information. Fortunately, the consequences weren't too catastrophic. Communication technologies were just beginning to develop at that time. But what would happen if such an event occurred today? Many experts have estimated that the damage from a similar storm in the United States could reach up to $2.6 trillion. The entire internet would shut down. For a while, we would lose access to our messaging apps, our banks, our navigation systems. Contactless payments, airports, train stations, and much more would stop working. We would be cut off not only from the internet, but also from electricity for a long time. The entire planet would be plunged into darkness and silence. A global economic and humanitarian crisis would begin. It's hard to imagine the damage that AI would suffer. But don't worry, the good news is that storms like this happen roughly once every 500 years, and smaller ones about every 50 years. But these aren't precise forecasts, since it's quite difficult for scientists to predict the sun's behavior. Besides, we wouldn't just sit in shock after such an event, we would immediately begin dealing with the consequences. The impact on modern civilization from such a storm would be significant, but we would surely recover quickly.
Australia has 5 major cities: Sydney, Melbourne, Brisbane, Perth, and Adelaide. Every one of them sits in the southern half of the continent. The northern 40%, an area bigger than most countries on Earth, has none. There are towns up there, along with ports, mines, and harbors, but not one major city, not a single one. That northern part of the continent only holds around 5% of Australia's people. Its largest centers, Townsville, Cairns, and Darwin, top out between roughly 150,000 and 200,000 residents. Sydney and Melbourne each have more than 5 million. So why has a country this wealthy never built a major city in its own tropics? On paper, it should be perfect, tropical, coastal, the closest part of Australia to Asia, but rain is the problem here. Darwin has 2 reasons, not 4. The dry from May to October and the wet from November to April. It gets about 68 inches a year, nearly 3 times what London normally gets, but almost all of it dumps during those monsoon months, flooding roads and cutting off whole towns. Then the tap shuts off, and the tropical heat evaporates whatever's left in the reservoirs, so the north spends half the year drowning and half of it thirsty. Then there's the heat and the humidity. Picture it, sweltering, standing on a beautiful tropical beach, every instinct telling you to jump in. You can't. Since hunting was banned in 1971, the territory's saltwater crocodiles have exploded from about 3,000 to over 100,000, up to 8 per mile of waterway. And in the wet season, the water fills with dangerous box jellyfish.
Hey, hit subscribe.
Then the weather at its worst. Darwin has been flattened twice in living memory, once in the 1940s and again on Christmas morning 1974, when Cyclone Tracy struck with 135-mile-per-hour gusts, destroying over 70% of the city and killing 66 people. Most of the population had to be evacuated. Many never came back. And finally, distance. Darwin sits 1,900 miles from the nearest major Australian city. Everything costs more to build and ship, so business clusters where the people already are keep the south growing and the north small. So, could Australia ever build its first major northern city? Let's play it out. Water is about storage. Build covered reservoirs and pump wet season floodwater into underground aquifers, desalinate along the coast, and the wettest corner of Australia stops being the thirstiest. Heat is really an energy problem, and the north has some of the fiercest sunlight on Earth. Cheap solar makes cooling cheap. As for cyclones, it's partly solved already, since the city was rebuilt to strict codes after Tracy, which leaves distance. It only counts against you if you're measuring toward Sydney. Measure toward Jakarta, Singapore, Manila, hundreds of millions of people hours away, and the empty north stops looking like Australia's back door and starts looking like its front one. Why is 95% of Australia empty? We all know the standard explanation. The Australian outback is a burning hellscape full of deserts and deadly spiders. And sure, that's true. But there is a deeper reason. It isn't just a geographical accident. It's a calculated economic strategy. Australia isn't empty because it failed to conquer the land. It's empty because it chose not to. Here's the reality. Filling this land with people would be financial and ecological suicide. First, look at the water. Could Australia terraform the desert? Technically, yes. They could divert rivers and pump aquifers to build green cities in the center, just like the Soviet Union tried in Central Asia. But look at what happened there. The Aral Sea dried up, creating a toxic dust bowl. Australia learned from history. The government knows that the interior's water, like the Great Artesian Basin, which covers a massive 1.7 million square kilometers, is a finite battery, not a renewable river. Large-scale settlement would drain it in decades, leading to collapse. So they intentionally restrict development to keep the system stable. Second, emptiness is actually profitable. The outback isn't a wasteland. It's an industrial engine packed with iron, gold, and uranium. But modern mining doesn't need cities, it needs automation. Australia runs some of the world's largest mines, with the autonomous trucks and robots controlled from air-conditioned offices in Perth, over 900 miles away. Building cities for workers in the middle of nowhere makes no economic sense. It's cheaper to fly staff in for 2 weeks and fly them out than to build schools, hospitals, and suburbs in a desert. The emptiness allows for maximum extraction and minimum overhead. And finally, there is the tyranny of distance. Infrastructure costs in the outback grow exponentially. Maintaining a mile of asphalt road or a power line in 50-degree heat costs a fortune. If you build a city in the center, you have to subsidize every drop of water and every watt of electricity forever. By keeping the population hugged tight to the coast, Australia creates one of the most efficient economies on Earth. They don't fight the map, they accept it. So, why is 95% of Australia empty? Not because the land is useless, but because leaving it empty is the only way to keep the country rich.
Australia feels like the safest place on Earth, geologically speaking. No megavolcanoes, no massive fault lines slicing cities in half, no constant earthquake alerts. It looks solid and unbreakable, but according to a brand new global stress map of Earth's crust, Australia is one of the most internally stressed pieces of land on the entire planet. It's not shaking or cracking yet, but it's quietly storing energy like a bent ruler about to snap. To understand why this is such a big deal, imagine Earth's crust like a giant jigsaw puzzle made of moving slabs called tectonic plates. These plates float on softer rock below and push, pull, or grind against each other. Where plates meet, earthquakes and volcanoes make sense. But stress doesn't just stay at the edges, it travels. It builds up inside plates too, like pressure spreading through frozen ice when you squeeze it. Scientists mapped over 100,000 real stress measurements from oil wells, rock tests, and earthquakes to see where Earth is being squeezed the hardest right now. When they laid all the data together, the map lit up like a warning sign, and Australia stood out. This shocked scientists because Australia sits far away from plate boundaries, which usually means stability. But instead of relaxing, the Australian continent gets squeezed from multiple directions by nearby plates, especially the Pacific and Eurasian ones. The stress doesn't release easily, so it piles up inside the crust, and then nothing moves. Until suddenly everything does. One of the strangest discoveries showed up in places like the Bowen Basin, where stress directions twist and rotate underground. That's bad news because unpredictable stress behaves like glass about to shatter. These rotating stress fields make it nearly impossible to say when or where cracks could form. It could be years away or tomorrow. And human activity makes it even riskier. Drilling deep into the crust for geothermal energy or injecting fluids underground can nudge these stressed zones just enough to trigger fault movement. This doesn't mean Australia is about to split in half next week, but it does mean the idea of geologically safe might be outdated. Scientists now think Australia could eventually fracture internally and form new fault systems where none existed before. What makes the new stress map different from older models is that it doesn't just explain past earthquakes, it helps identify future risk zones before anything breaks. Countries can use this data to decide where drilling is safer, where tunnels shouldn't go, and where infrastructure needs reinforcement. But even with all this data, we still can't predict the exact moment Earth will snap. Stress maps tell us where the tension is. They don't tell us when it gives up. But this idea of continents quietly tearing themselves apart isn't just theory. Africa gives us the clearest real-world example. It's slowly unzipping itself. So slowly that no human will ever wake up and see a new ocean where land used to be, but fast enough that scientists can actually measure it happening right now. Deep beneath East Africa, the ground stretches, thins, and pulls apart as if the continent is taking a deep breath and never fully exhaling. And over millions of years, that stretch could turn into an ocean. This whole process centers on something called the East African Rift System, or EARS for short. Think of it like a giant tear running through the continent, thousands of miles long, cutting through countries like Ethiopia, Kenya, Tanzania, and Mozambique. It's one of the biggest rift zones on Earth. A rift zone is exactly what it sounds like, a place where the planet's crust is being pulled apart instead of squeezed together. And Africa just happens to have one of the most dramatic examples anywhere on the planet. What's really happening is that Africa isn't one solid plate anymore. It's splitting into two massive chunks, the Nubian plate to the west and the Somalian plate to the east. These two plates are drifting away from each other at a speed that sounds laughable, just less than an inch per year. That's about the speed your fingernails grow. But give that process millions of years and suddenly continents don't look so permanent anymore. In 2018, photos of a giant split in Kenya went viral across the internet. Headlines screamed that Africa was splitting in half right now. It looked dramatic, but that moment didn't mean Africa suddenly broke overnight. That rupture was more like a surface ripple, a small local sign of a much bigger process that's been going on for around 25 million years. And if we could travel in time to 5 or 10 million years from now, we would probably see the crust thin enough for seawater to rush in. When or if that happens, East Africa would slowly peel away from the rest of the continent, and a brand new ocean basin would form between the two plates. Africa would lose its eastern shoulder, and maps of the world would need a serious update. As strange as that sounds, it's actually totally normal for Earth. The planet never stops reshaping itself. It just works on a timeline so slow that our brains struggle to process it. The continents we know today feel ancient and permanent, but they're basically temporary arrangements. About 138 million years ago, South America and Africa were locked together like puzzle pieces. You can still see it if you look at their coastlines. They match almost perfectly. East Africa drifting away will just be the next chapter in that story. Australia's story could follow a different path, but the physics are similar. Stress builds, rock resists, then the rock fails. And stress doesn't care about borders, cities, or how calm the surface looks. That's why scientists are so concerned about something called SH max, the direction of maximum horizontal stress. In simple terms, it tells us which way the Earth is squeezing the hardest underground. If that squeezing lines up with existing fractures, earthquakes become more likely. If it cuts across old faults, new ones can form. Turkey is another place where the stress map practically screams danger. The country sits where Arabian, Eurasian, and African tectonic plates collide. There's also a smaller Anatolian plate on which Turkey is located, and which gets squeezed westward like toothpaste, grinding against massive faults. The stress map shows SH max pointing in directions that load these faults perfectly. Now, researchers looked at ancient lava flows near one of Turkey's faults and realized they weren't random. Lava sheets once flowed smoothly across the land, cooled into solid rock, and then got pulled apart over time, like a snapped chocolate bar. That gave scientists a rare, clear snapshot of how continents deform from the inside out. To date the lava, the team used microscopic zircon crystals trapped inside it. These crystals work like natural stopwatches. They trap helium created by radioactive decay, and by measuring that helium, scientists can tell when the lava erupted and cooled. When they combine that with satellite images and remote sensing, the scientists managed to see Earth's slow-motion movements. The Tuzgolu Fault stretches more than 120 miles and is so massive that you can spot it from space. For years, scientists assumed it behaved like many of Turkey's dangerous faults, where land slides sideways past itself. But this new research flipped that idea on its head. The fault isn't sliding, it's slowly ripping open. The land on either side moves away from each other at less than an inch per year. That sounds tiny, but then again, over thousands or millions of years, that motion adds up to continents literally thinning and breaking. And since the fault sits where three massive tectonic plates meet, this matters way beyond Turkey. All this once again reminds us that continents don't just collide or slide. Sometimes they stretch until they snap. And places that look calm on the surface might already be under invisible strain, inch by inch, year after year, rewriting the map long before anyone feels the shake. Usually, we associate living below ground with poverty or bunkers, a last resort for those with no other options. But in this specific location, the logic is flipped upside down, as living underground is the ultimate luxury. Zoom in at this spot. Plenty of mounds, holes, and almost no buildings, trees, and people. This isn't a ghost town. In fact, we're in South Australia at Coober, Pedy, the opal mining capital of the world. And here's the kicker. About 60% of the town's population lives underground. On the surface, Coober Pedy is unforgiving territory because of the severe weather. In the summer, temperatures regularly hit above 50 degrees Celsius. It's so intense that electronics fail and birds are literally falling out of the sky from heat exhaustion. To cope with it, people of Coober Pedy often play golf at night using glowing balls to avoid sunlight. There's the only golf course without a single blade of grass in the world. If you live in a standard house above ground, your air conditioning bill can cost a fortune, and if the power goes out, the heat becomes life-threatening. Where's the ultimate solution? To go down even just a few meters into dugout homes carved directly into sandstone. Down here, the temperature stays at a perfect, constant 23 degrees Celsius all year round, without any artificial cooling. These aren't dark caves. They are full-scale homes with kitchens, Wi-Fi, and living rooms, just without windows and air conditioning. What else you may need in your town, even though it's underground? Bars with pool tables? Sure thing. Bookstores? Of course. And they even have this beautiful church carved entirely out of sandstone. On the other hand, there is a complex, often forgotten, bitter part of the story. While many miners with their families live in these kind of cool sandstone structures, a significant group of the local indigenous population remains above ground. Yes, the government provides proper houses for them, but they're often the worst places to be because despite being modern, they can trap heat and act like ovens in this climate. And here comes this strange paradox. The primitive method of digging a hole is actually the most sophisticated and luxurious way to survive in this desert, while the modern solution of building a house can be a real nightmare for the residents. We're seeing empty desert on a map, while in fact looking at the only thing that can save people from severe sunlight, the ground itself.
So a few years ago, in 2019, folks in Australia said they liked an old idea with a new twist, using extra floodwater from the north to help dry areas in the west and south. This plan got the name of the New Brainfield Scheme. It was based on an old idea from the 1930s. The idea was to catch floodwater from the north and move it to the south and west. But the original plan never actually happened. Over the years, lots of experts said it wouldn't work. They thought it was too expensive and too tricky to build, even though it could potentially help fix drought problems in dry parts of Queensland. The original idea appeared a long time ago, when an engineer named John Brainfield got a big idea. He wanted to take floodwater from rivers in northern Queensland and send it inland to Lake Erie, one of the driest spots in Australia. He planned to use dams, pumps, really big pipes, and even tunnels to transport all that water over the Great Dividing Range, a big mountain range in Australia. The biggest dam would have been called Hell's Gate, and Brainfield wanted it twice as tall as what it was originally planned. This way, pumps and gravity could help move the water over the Great Dividing Range. The water would then flow south and help irrigate farmland near places like Hughenden. It would change the weather, make it rain more, and turn the dry land into green farms. Eventually, it would reach Lake Erie, turning the desert into a green growing area. That way, Australia could grow more food, sell it to other countries, and make more jobs. He hoped that the area could turn into a food bowl for the country. For some time, people talked about the plan a lot. They loved the idea. They thought it could change how farming worked. And some even believed that nature had already planned for the land to be filled with water. Dry rivers and lake beds were just waiting to be used. They even said that rains fell on the wrong side of the mountains, and Brainfield's plan could fix that. But when the authorities looked into this idea, they found big problems. And the main one was that the plan would cost too much. Plus, there weren't enough scientists or engineers to do a full investigation. The land was too dry and harsh. No one was sure it would even work, like how much water would really get there. Plus, some of Brainfield's measurements were wrong, especially the dam heights. So, in 1947, they officially shut the project down, claiming that even if they built the project, it wouldn't be worth it. After all, even places next to oceans, like parts of Chile, still stay bone dry, so a big lake might not result in more rain. And still, in 2019, one political party brought the idea back with an updated version called the new Brandfield scheme. They wanted to try it again, but with some changes to make it work better. Their plan included the following steps. Take water from the South Johnstone, Tully, Herbert, and Burdekin rivers. Store that water using a big dam called Hell's Gate Dam, but this time they wanted to make the dam twice as tall as in the original plan. Let the water flow through tunnels using gravity instead of using lots of pumps. Move the water under the mountains and into the Warrego River in southern Queensland. Use the water to grow crops in dry places south and west of Hughenden, a huge area even bigger than Tasmania, eventually turning it into a food bowl. At the same time, they didn't say how much the whole project would cost, but they promised to spend $20 million to let Australia's National Science Agency check if the plan could work. Those innovative ideas sounded good, but for over 80 years, loads of experts kept saying, "Nope, it won't work." Why? Brandfield said his idea would cost £40 million back in 1941. That's about $3.2 billion today. But the new version of the plan might cost more than $15 billion and take over 10 years to build. Also, people who care about nature are worried. They explain that taking water away from where it usually goes could hurt animals and plants. It might let invasive plants and animals spread to new places. It might mess up rivers and oceans, where fish and other animals live. It could even hurt towns and businesses near the coast that depend on those natural water flows. Still, some people really believed in the idea and thought it was worth doing, especially to help farmers and fix drought problems. However, in 2022, the government decided to stop trying to fix the drought in western Queensland with the Brandfield scheme. Experts looked closely at the plan and said it just wouldn't work. The problem? There's not enough water all the time to make it happen. Apparently, the new cost of the plan would have been over $30 billion. That's a huge amount of money. You could buy yourself a fleet of private jets and luxurious yachts, and more. So experts said you'd need lots and lots of water to spend that kind of money, but the water just isn't there. Now, instead of one huge project, they suggested doing smaller water projects closer to where the rain and waterfalls are. These smaller projects, called mini Brandfield grids, would be in 4 places along the Queensland coast. Those little grids could share water when some places had more or less rain. Other scientists looked at the plan too, and they agreed. Even if things went super well, the Brandfield scheme would still cause problems and cost way too much, while the mini water grids project looks more plausible. They think the dry parts west of the mountains will do better without the full-scale Brandfield scheme. There are easier and cheaper ways to help those places grow and get water. So the big plan was dropped, and now they're looking at smarter, smaller ideas to help with water and farming. And the matter is quite urgent. Australia is a super dry place, one of the driest places people actually live in. When there's a drought, there's not much water around. That means farms don't grow as much food, and that can cause a lot of problems. In the future, droughts are likely to happen more often and be worse. That's why it's necessary to start getting ready now. Experts are working on something called the Drought Resilience Mission, trying to figure out how to deal with droughts better in the future. One of them looked at how much droughts actually cost Australia. His research shows that droughts can hurt a lot of things – farms, jobs, towns, and even the whole country. When there's no rain for a really long time, some towns can actually run out of water. That's called day zero. It's when the taps in people's houses get turned off because there's just no water left. In 2020, a town in Queensland called Stanthorpe hit day zero. About 50 other towns were really close too. When such a situation happens, the only way to get water is by bringing it in with trucks, and that's super expensive. Stanthorpe had to get around 20 trucks of water every day for a year and a half. It cost them about $800,000 every month. In the end, they spent over $14 million just to have water. Luckily, it started raining again and filled the dams back up. But the authorities are working on ways to stop this kind of thing from happening again. They want to help towns be ready so they never run out of water like that. Because drought just doesn't mess with water, it can also mess with people's health. When everything dries up, plants vanish and the soil gets loose. Then the wind picks it up and makes huge dust storms. Those dust clouds can blow really far, even into such big cities as Sydney. That's what happened in 2018. The air got so bad that kids, older people, and anyone with breathing problems had to be extremely careful. The dust ruined some crops and made different foods, even fruit, unsafe to eat.